Okay, so this is section 6.3 if you are a textbook reader. And this, when we do this, it seems really obvious what the question's going to be asking, but there's sort of a procedure to it. So when you take a look at these questions, they get progressively more difficult, okay? So I even wrote a note for myself, make a harder example, which I didn't do. So make sure you try number 6, okay? Because it's definitely harder. And it's not even about is it hard, is it not hard, whatever. You just have to kind of remember the procedure to do this, okay? So when we have a rate law, so we are going to be, for a rate law, we're going to be looking at how the rate is affected by the reactants only, which makes sense. It's easy to know as a scientist how much reactant you're putting in. It is an exponential shape, which we just saw, right? It's not a straight line. So when you're asked to write a rate law, it's going to connect the concentration of the reactants only. And so today we'll look at how you can use data to figure out the rate law. And then Monday we'll use the reaction, or when you come back Monday, we'll use reaction mechanism and the rate determining step. So in general, the rate law, you're always going to have rate on the left. I'll talk about what K means in a second, but that's called the rate constant. And then however many reactants you have, and again, that's going to be their concentration. So this random equation, A plus B, then it's concentration of A times the concentration of B. So it's all multiplying, okay? And raised to some exponent. So you saw the exponential shape of the curve. So we need a way to figure out, okay, what are the exponents? Or changing the concentration of A or B, how is that going to affect the rate? And if it's got an exponent that's not 1, so 0 or 2 or 3 or whatever, then things can get really fast, really quick, or conversely really slow. So again, Maria's chemical factory, she needs to know which concentration is going to have a bigger impact on the rate. So the rate constant, mathematically, this is called the integrated rate law, so it definitely has connections to calculus. So the rate constant is a number that is going to tell us how fast the reaction is. So if you have a large K, then the reaction is faster, and then a smaller K means that the reaction is going to be slower. And again, you can think of that like if you have a big number here and you're multiplying, that's going to make your rate bigger. If you have a small number here, then it's going to make it smaller. So you need a considerable amount of information in order to figure out what the K value is, but you can do it, which we'll do that today. Okay, so we're going to determine the exponents in the rate law. And the exponents in the rate law are going to help us with what's called the order of reaction. So if you have an exponent that is going to influence how much that reactant concentration will influence the rate of reaction. So what we call that is the order of reaction. And then the total order of reaction, you just have to add them together. So then if you have a reaction that has a certain total, so say the exponents are 2 and 1, and you add them together to get 3, then and you talk to another chemist, a third order reaction, then they know what that means about how steep or how deep the exponential curve is going to be. So it can be used to, like in general, predict what the rate is going to be. So here, if you're given this rate law, the order of reaction with respect to A is 3 and B is 1. Where did I get that from? It's just the exponent. The total order of reaction, just add them together. Similar to a lot of the topics in this unit, we're going to deal with whole number exponents only. There's definitely a way to deal with exponential equations that do not have whole numbers using logs. But again, because functions is not a prerequisite, then you can do that next year, okay? So you can also be asked questions like this. Again, we're trying to predict the rate. So how would the rate be affected? We're just going to predict it. So when you have the rate law, and you can actually do this separately if you want. You can do it together. So we'll do B first. Okay, so B is going to be doubled. So whatever B is, doesn't matter. If we double the concentration of B, and even just use a 2. So let's say we started at 1, we went to 2. When you do 2 to the power of 1, that's just a linear change. So then you're doubling the rate. When you do A, what's A's exponent? 3. So no longer a linear change. So whether you increase it or decrease it, this is going to have a much bigger impact on the rate than this because of the exponent. So here, you know what? Let's do this. We'll make it doubled for a second, okay? So now if you double A, what would you actually be doing to the rate? What's 2 to the power of 3? Yep. Rate would be times 8. It's 8, right? Yeah. Okay? So that, and you know, and you can think of that mathematically, you would know this, right? That the exponent is going to influence how fast the curve or whatever changes. You could also do them together, okay? So I'm going to go back to the quarter for a second. So you could do it together. So A was, let's say it was quarter A, and B was doubled. Really, what would happen, what's a quarter cubed? I'm going to leave it as a fraction, okay? So 1 over 64 times 2, basically. So again, when you decrease the rate, it also has a huge impact, or decrease the concentration, it has a huge impact on the rate. So do we know what the rate is? No. Do we know what it started at? No. We're just using this to sort of predict what could happen to the rate. So if this bothers you, like 2 over 62 1 over 64 times 2 becomes 1 over 32. So the rate would actually be decreased 32 times, like this is like divided by 32. If you don't like this, then you can just separate it every time like that. That's fine. We're just using it, we're using the rate law to sort of predict how the rate could be affected. Okay, so how do you find the rate law? So we can use experimental data to find the mathematical relationship. So the good news is when you have to do this, you have to be given the data. So it looks very unique. So you can see there, you have to be given a chart with data in it. Now, again, unfortunately for those of you that hate scientific notation, your textbook loves it. Okay, so usually often they will use scientific notation. In the past, kids have literally been on the test like, please don't give us scientific notation. So I think I try not to, but when you do the questions, especially number 6, it is going to be probably scientific notation. Okay, so, but I can show you, if you have your calculator here, I can show you how to do it. No problem. Okay, so you have to be given the concentration of the reactants, every single reactant. You have to be given also the rate, because what we're going to do is we're going to look at how the rate is influenced by changing the concentration. So they call it here a run. Sometimes it'll be called like a trial. So what they've done is the scientists have run or done this reaction 3 times. The first time they did 0.4 molar NO and 0.1 molar H2, and then they got a rate of 1.1 times 10 to the negative 5. Then they did 0.4, they kept that the same, but they changed this one, and the rate got different. And then they did 0.8 and 0.2. So now these two are the same, this one's different, and they measured the rate of reaction. So what we're going to try to do is look at when you change the concentration, how does it affect the rate? So because this has 2 reactants, and again, number 6, I think there's 3, maybe even 4, okay? When you have 2 reactants, then if they're both changing, then you can't decide how is one of them affecting the rate. Is it the first one? Is it the second one? You don't know. So if you'll notice, here, this is the same, but this isn't. And then here, this is the different, but this is the same. So that's what you're looking for. You're going to pick runs or trials to look at where only one concentration is changing. The other substance or substances aren't. Okay? So these happen to be back to back. You can do like 1 and 3 because it doesn't really matter what order these are in. They just did the same reaction 3 different times. They changed the concentrations and got different rates. It doesn't matter, 1, 2, 3. There's no order to it, except they have different concentrations and a different rate. Okay? So what I'm going to do, I'm going to write steps in general, and then I'm going to do the work on the right-hand side. Okay? Actually, we're going to write in general, what the rate law is. So again, it's always rate on the left. Put the K in, don't forget the K. And then however many reactants you have, raised to some exponent. So if it's practical, usually there's 3, or the maximum is 3. On a paper and pencil task, if you're just using A and B, really you could put whatever, like not real elements, you could put whatever you wanted. So however many reactants there are, that's how many spots you would have, okay? We're not worried about the products, we don't care about those. And we're not given any data for the products, okay? So when you're given the data, it's going to tell you, this is NO, here it is. This is H2, here it is, okay? It's not going to trick you and give you data that you don't need. So there would never be a column for the products and you would never have to figure out, is it a reactant, is it a product, am I supposed to use this data? No, they'll just give you the data for the reactants. So in this case, they are going to be consecutive, okay, but it doesn't have to be. And it doesn't matter which one you start with either. Most people will want to do NO first because it's the first one listed, but you don't have to. You could do H2 first because it's all multiplying. You could even put H2 in the rate law first, and it does not matter. What matters more is that you have the rate and the K general part of the equation, and that you have the reactant concentration with its correct exponent, okay? So, but I'll stick with this one. I'll do NO first, okay? So I called this number 1, so over here I'm going to write number 1. All right, so for NO, then here, NO. This one is not changing, so that's not helpful because that means that NO, whatever change is happening with the rate here is not because of NO. I don't like that. So between 2 and 3, that one is changing. So, okay, I like this, but then you have to check. Is H2 not changing? Oh, good, it's not. So I'm going to use 2 and 3. And sometimes students like to do this. right on the chart. Now, it's unfortunate in your textbook if somebody has done that before you, then it kind of, can lead you either to the answer and then you don't get to practice, or maybe they've done it wrong and they lead you astray, but that's okay. We're not going to worry about H2 for a second at all. We just want to make sure that it's not changing, okay? So between 0.4 and 0.8, what is that? How's it changing? Pardon? Oh, yes. It is adding 0.4, yes. However, we want to use a whole number. So what I would do is just take the bigger one and divide the smaller one. You're right though, Maria. If you did it upside down, 0.4 divided by 0.8, you would get 0.5. So again, no decimals, okay? So don't add, but that was good. And don't divide the bigger by the smaller. I mean, the smaller by the bigger. Do whatever's the biggest one divided by the smaller one. So remember, this year it's going to work. So, and there's not very much variety. Maybe it'll be doubled, maybe tripled, maybe quadrupled, but that's really stretching the limits. Normally, it's mostly just doubled. Okay? So some people will even write it on here like this. Then we need to calculate how the rate is changing. For these two, if it's not obvious, maybe even write it down that you have to, once you've chosen the two runs or the two trials, that's the ones you're looking at for the rest. Okay, so if you want to add that in. So not random ones, okay? The ones that you chose in one. So now we did concentration. Now we're going to do rate. And once you decide, like I did this, 3.8 divided by the run 2.4, you can just do the same thing over here. Or again, it's going to be bigger divided by smaller. So again, you'll see people do this. So 4 and 2 are numbers that are closely related. So again, it has to work. So if it's 3, then it would be 9 or 27. Okay, so if it's not something that is a multiple of the other number, then again, you've made a mistake. Okay, go back and check again that you've used the right trials. So maybe you've chosen one where more than one concentration is changing or something like that. Okay. So I need to write how the rate is changing, the factor, the 4, as a power of how the concentration is changing. Or I want to write 4 as a power of 2. So this one here has to be the base, and then you need to write this one with a base of 2. So what's 4 as a power of 2? Yes. This is an S, sorry. Okay, so it has to work. We're not going to use logs this year, okay? So if you can't do that, then go back and check what you've done, okay? I promise there's no tricks. It's not going to be like, oh, this rate law won't work. No, it should work, okay? So now that we have a number with an exponent or a power, then that means that whatever exponent is here, that is going to be the exponent on NO. So when it is not a linear change, you've changed the concentration of the NO, it has had a bigger impact on the rate than just a linear, like to the power of 1, okay? Now, it is unfortunate because 2 to the power of 2, those look the same. But whenever you do this, you want to look for the exponent. That becomes the exponent, which does sort of make sense. So it's not the base, it's the exponent that you're looking for. Okay, so I'm going to do the other one. I'm going to do age 2. I'm going to number them the same, but I'm not going to write this out again, okay? So when I switch the slide, I'm going to have a blank chart, but I'll write this on here like I did here. You can just write it on the same chart. That's what most people will choose to do, okay? We good? So first, I have to choose 2 runs where only H2 substance is changing. So between 1 and 2, this NO stays the same, but this H2 changes right here. Let me just see how I wrote it over here. They should not be the same. If the substance is if you're trying to use the same 2 runs or 2 trials, then that's not going to work, okay? then there would be no effect on the rate, or you can't tell the difference. One of them has to be changing and the other ones cannot be, okay? So now again, decide or calculate how it's changing. So again, maybe this one you can see, oh, that's doubled. You don't need to do the math, which is fine. Again, lots of people will write it up here. Then we do the same thing for rate. Okay, so now this one is even more straightforward. However, you would be surprised at how many people will write that the exponent is 2. So I really recommend that you show your work. What is 2 as a power of 2? Yes, 2 to the power of 1. Then emphasizing that this is the exponent that you need, okay? Please, 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 don't do all this work and forget to write the rate law, okay? Technically, we haven't answered the question yet, right? So it takes the general form, rate equals K, just put the K, it's a constant, NO and H2 are the reactants, and we just figured out their exponents. NO was 2, H2 was 1. Well, you don't have to write the 1, okay? I highly recommend it to emphasize to yourself, okay, that's the exponent. It comes from here, okay? Because lots of people will write that the exponent is 2, and it's not. We're not looking at the base. We're looking at what the exponent is. Okay, I want to do one more sneaky little thing, especially those of you that are thinking about taking the AP exam. So you guys can just keep going. I need to use this data. Do I have? Oh, I do. Never mind. So you can, now that you have the rate law, you can solve for K. And the math part of it is pretty straightforward. It's the figuring out what units you have for K that is tricky, okay? If you've done the work, like if you got the right rate law, and so you have the correct exponents, it doesn't matter which run you use, but you have to use a complete run. You can't go, I'm going to use this concentration, and this rate. That's not how it works. So most people just pick run 1, but it doesn't really matter. We have a rate. We're solving for K. We have concentration. So again, decide for yourself. Do I want to do this, do BEDMAS, like exponents first, then multiply, then divide? If you prefer, you can divide. You could have up here rearranged and divided by the concentrations. It's really up to you. You do need to make sure, that you do this part first before you divide. So we get a pretty small K, which means this reaction is not fast. Okay, so here's the units. So if you want to just watch for a second, I'm going to use this line. So I'm going to write it here, but it doesn't really matter. Okay, so we've got moles per liter second. That's what rate is. Divided by moles per liter. And moles per liter. So all I've done is taken this line and written it just with units, okay? So you have to remember some basic principles about multiplying, dividing, exponents, okay? So if you divide fractions, you have to flip and multiply. Times. So now the liters are going to be in the top. But this is like moles squared, liters squared times moles per liter. So that makes it if this was x squared and x, you would add the exponents, right? So you have to remember your like grade 9 exponent laws. And now things will cancel. So we have liters and liters, but there's 3 of them, only 1, so you get 2. Moles. Okay, so that is liters squared per seconds mole squared, or if you prefer mole squared seconds, whatever. So this is really sort of an aside, I guess. Every single third order reaction, so 2 plus 1 is 3, will have these units for K. So the units for K can be an indicator of the order of reaction. So like I said, those of you that are taking if you're considering taking the AP exam, they might be stickly about that. Okay, so these questions, remember 3 and 4, not too bad. 6 is much. I think, like I said, I think it has 4 random reactants. It's a huge chart. The person who had your textbook before probably wrote all over it. Try to erase it before you look at it. Okay, so at least try this one. Okay, so